Hello, and welcome to Einstein Educates. My name is Albert Einstein. I wish to discuss with you a topic that is near and dear to my heart: equilibrium. Equilibrium is defined as the exact balancing of two processes, one of which is the opposite of the other. Kind of like the relationship between me and my wife, but that's another story. Equilibrium is one of the most important aspects on Earth. From the function of automobiles and medical respirators to the use of a simple water gun, equilibrium is of paramount importance. It even affects dynamics outside of Earth, like star formation. But for you simpletons out there that don't have an IQ of greater than 200 like myself, here's an example. Let's imagine Mr. Carter, an upper school science teacher at the Park School of Baltimore, decides to take his favorite chemistry class to the track for a demonstration in equilibrium. He tells the group they will be using the fraction 1/4 to determine how many will run past the cone and stop opposite them. It is important to note that fractions of people count as a whole person. In layman's terms, do not cut people into fractions of themselves. I do not think they would like that at all. So we will begin with 10 people at the starting line. 1/4 of them, which is 2.5, but will get rounded to 3 due to the non-fraction rule explained earlier, will run to the cone. Because this is done at the same time, there is no one at the cone when people are sent, so 1/4 of nothing is 0. Now we have 7 people at the starting line and 3 people at the cone. We then take 1/4 of 7, so we send 2 people, while those at the cone send 1/4 of 3 people, which is 1. At the end, we have 6 people at the starting line and 4 people at the cone. Finally, 1/4 of 6 or 2 people are sent to the cone, while 1/4 of 4 people or 1 person is sent back to the starting line. We now have an equal amount of people at the starting line and at the cone. No matter what, we will always be sending the same numbers as we are receiving. This is equilibrium. Fascinating, isn't it? Let's move on. When scientists think about equilibrium, they refer to chemical equilibrium. This is represented by the constant K-E-Q. Chemical equilibrium is a dynamic state where the concentration of all reactants and products remain constant. Let's use the following example to explain. In the following formula, nitrogen gas reacts with hydrogen gas to produce ammonia. The forward reaction towards production of ammonia takes off fast. Many molecules of ammonia are produced. However, as the reactants are used up, the forward reaction slows and ammonia begins to be converted to the reactants. Eventually, the number of molecules of reactants equals the number of molecules of the products. Eureka! Chemical equilibrium!
So what we did was we took 500 milliliters of water, put that in a 3-liter bottle. Then we took 36.2 grams of aluminum foil balls, which is approximately 60 to 90 small aluminum foil balls. And then we put in 156 grams of crystallized Drano. And as soon as we put the Drano in, we put on the top to the bottle, tightened it as hard as we could, and then shook the bottle and ran out of there, because you do not want to get caught in what is about to happen.
Whoa! That was quite an explosion! So, Pseudo-Professor Perry, would you care to explain the exact science behind this?
Sure, no problem, Einstein. So, assuming that Drano is made primarily of sodium hydroxide, which it is, we'll say that the equation for Drano is 2NaOH plus 2Al plus 2H2O yields 3H2 plus 2NaAlO2. So, we want to find the equilibrium constant for this reaction. In order to do this, we take the concentrations of the reactants and the products, then we divide the concentrations of the products by the concentrations of the reactants, and that gives us the equilibrium constant for this reaction. So let's test this out. The concentration of sodium hydroxide is 7.78 molar. The concentration of aluminum is 2.37 molar. The concentration of sodium aluminum oxide is 7.73 molar. And the concentration of hydrogen gas is 11.7 molar. Now, take into account that this is all experimental values because it's not like we can really measure the actual amounts. So we take those values and use the equation that I mentioned before, and that gives us 95,701.02 over 341.73, which is 2.80 times 10 squared.
Thank you for your insight, Pseudo-Professor. And to our audience, thank you for watching. See you next time on Einstein Educates. Goodbye.